Hey there and welcome to another LeetCode problem. So today we're going to be doing problem number 2709, greatest common divisor traversal, and it's from the biweekly LeetCode contest for today actually. And it was the hardest problem on there, worth 6 points. So let's take a read. You're given a zero index array nums, you're allowed to traverse between its indices. You can traverse between index I if it doesn't equal j, only if GCD of nums I as j is greater than or equal to 1. Where GCD is the greatest common divisor, your task is to determine for every pair of indices is there a sequence of traversals that take us from I to j. Return true if this is possible. Okay, so first of all, let's try to figure out, this problem is going to be broken down into multiple steps. Let's do the first step. So in order for there to be a sequence of traversals that take us from I to j, right? So let's say we have index 0, 0, 1, 2. In order for there to be a sequence of traversals that take us from here to here, you have to recognize that this is a graph problem, and you have to know that in order to traverse from the front to the end, these nodes have to be connected, at least minimally connected, right? So there could obviously be like multiple paths, but at the very least, all of these nodes have to make one connected component. So for example, if you have 4 nodes, like this, there has to be some kind of path to go from one node to the rest of the nodes, meaning that every single one of these nodes is connected, and so the number of connected components in this graph is 1. And so for connected components, something good to use is union find. So let me just briefly describe union find. I'm not going to go over all of my code, but I'm going to briefly describe what it does. So union find takes 2 nodes, and it has a couple methods. It has a find parent method, so let's just call that parent. Well, it will get the parent of each of these nodes. And the way a union find works is, let's say we have nodes like 0, 1, 2, and then we have some other node like, let's actually delete all this. So let's say we have node 0, 1, let's say there's node 2 here, and then we have some other node 3. And we try to connect node 3 to node 1, for example. Well, first of all, union find lets us check if they are already connected with a union method. So it has a union method, and it will return. You can do one of a couple of ways. You can either have it return false if it's already connected, or you can just have it not connect. But the way it works is you don't actually make a direct line from 1 to 3 if you want to make it connected, but what you do is you get the parent of each one. So the parent is let's just say these nodes are top down, so they're all going to look like this, where there's 0, 1, 2, and so on. You get the parent of 1, so the parent of 1 is 0, and then what you do is you connect the parent of each node to the parent of the other, and you connect the shorter node, right? So here, this would be the shorter node because this is the parent, like, it's basically the length of the link. So the length of this link is 3, the length of this link is 1. And so this node would be connected here. And so you wouldn't connect them directly, but you would connect it to the parent. So that's what union does. You take the parent of 2 nodes and you connect them. And then obviously parent of a node gives you that parent. So if I call parent on 1, it'll give me the parent. And all of these are just stored in an array. And I'm actually going to link the union find. There's a bunch of LeetCode stuff on it, so I'm going to link the union find on LeetCode in this problem because I don't want to go too deeply about it. But basically what it does is it connects 2 nodes, it can check if nodes are connected, and it can get the parent. So knowing that, let's say we do some stuff. We do some stuff to connect nodes somehow. How do we then check if there's a sequence of traversals? Well, it's actually pretty simple. So let's say we do have these nodes 4, 3, 12, 8. After we make our connections in the graph, how do we actually check if we can get from here to here? Well, it's pretty simple. All we have to do, so in the union find, there's also, remember I said there's a union, there's a find method, and there's a connected method. So connected. And what that method does is it simply checks if the 2 nodes are connected, meaning that the parent of the 2 nodes is the same. And I'll show you the code for union find, but I'm not going to code up the entire thing. I'll just briefly go over what it does in later. So all we have to do really is we just have to go through every single combination of 2 nodes next to each other. So like this, this, this. And we just have to ask ourselves, are they connected? So are these connected? Are these connected? Are these connected? And if every single group is connected, that means there is an edge in some way, there is a way to get from here to here, from here to here, from here to here. And because all of these are connected, that means this entire graph is connected. So that's going to be kind of our end goal. Once we make our connections, we're just going to union find, we're just going to go through all of these pairs of nodes, and we're just going to see if they are connected. And if a pair of nodes isn't connected, like let's say this isn't connected, in union find it means they're in two different components. And so what a component is, it's a sequence of connected nodes. So if 3 and 12 aren't connected, that means 12's over here and 3's over here, connected to some other stuff, and 12's connected to some other stuff. But you can never go from 3 to 12, meaning you can never go from the things that 3 is connected to the things that 12 is connected to. So this would return false. Okay, so that's part one of the problem, is how do we actually check if we're connected? And union find is going to be the best way of doing that. Now, the other part of the problem is, what's the most efficient way to actually connect the nodes, right? So we know that we can call union find on two nodes to connect the nodes, or it's going to be called union, but how do we connect the nodes? How do we know where to make the paths? And so in here, they're saying that there is a path where the GCD between two nodes is greater than 1, I believe, right? So for example, for this 2, 3, 6, let's just look at all of these nodes. Well, what we could do, one thing we could do is we can just have a nested for loop, right? So we could compare 2 to the nodes after it, 3 to the nodes after it. So what would that look like, and what would be the complexity, right? So we compare 2 and 3. GCD is the greatest common divisor, meaning the greatest number they can both be divided by. But here's another little trick. Because we only care about a number that's greater than 1, any number, if there's any number that's greater than 1 that they can both be divided by, then it would be a valid solution, right? So for example, if we have some numbers like 100 and 200, we don't actually need to get the GCD, which would be 100. If they're both divisible by 2, then that would be fine. Because the GCD is going to be divisible by some smaller number typically, right? So if they're both divisible by 2, that means the GCD is, it's going to be the GCD times some smaller number. Some smaller number is going to, or sorry, no, that's not going to be the case. It's going to be GCD is going to be two smaller numbers times themselves. Because the GCD can't be prime, right? Like if the GCD was prime, let's say it was 11, well then this wouldn't be divisible by 2. So the GCD would be A times B, where these are two smaller numbers. So that's all we really need to do to see if two nodes are connected. We don't actually have to check the GCD. We just have to check, is there some number greater than 1 that these are divisible by? And if that's the case, then we can make a path. And so, for example, yeah, for this 100 and 200, we can just illustrate that. So they're divisible by 2. Okay, well, so the GCD is actually 100. Well, 100 is divisible by 2, so what is that? That's 50. Well, that's obviously divisible by more stuff, so that's 5 and 10. And then the 10 is divisible into 5 and 2, and so on. So that's going to be the base case. Is all we're going to do is we're going to loop through numbers to see if they're divisible. But what would that look like? So if we do a GCD where we just try to figure it out, I think for GCD the time complexity is log n, because it's going to be a binary search, I believe. And so if you have to check every node and every other node, and then you just say, okay, is the GCD greater than 1? If yes, connect them. That's actually going to be n squared, right? And so if we look at these numbers, it's 10 to the 5th. So that would already be 10 to the 5th squared, which would be too big, times 10 to the 5th. And you can usually tell the way from these problems, if you have, these constraints are pretty common. I think I've said this in other problems. When these constraints are really big, usually an n squared solution isn't going to work. So you're going to have a n log n or something better. So what else can we do? Well, we can't just compare every node to every other node, but is there something else we can do? And so there is actually something else we can do, and we can get the prime factors of the number, and that's how we're going to do that. And then, so let's say we do get the prime factors. Well, what would that look like? So let's say we have a dictionary where the key is the prime factor. So let's just say this is some number. And then the value is the list of indices, right? So indices. And then all we're going to do is we're going to go through each node one time now. We're going to get all the prime factors. And then for every prime factor, we're going to add that index into the list of indices. So what would that allow us to do? instead of comparing every node to every other node. So for example, and for the prime factors, I mean every single number that is greater than 1. So let's just think of how we could, or what that would allow us to do, and then we're going to look a little bit into how we actually get the prime factors and why that's better than comparing every node to every other node. So let's say for 2, the prime factors is going to be 2. So let's just say this is this dictionary, right? And we'll have some keys and some values. Okay, so for 2, and then let's say these indices are 0, 1, 2. So the prime factors for 2 are just 2. So we're going to say 2, and then we're going to add node 0. Okay, for 3, the prime factors are just 3, right? So 3 is going to be node 1. Okay, and then for 6, it's 2 and 3. So we're going to add this 6 and this. Okay. And so what does this allow us to do? Well, what it allows us to do is, like I said, for the GCD, if 2 indices share, so a prime factor is a number that's greater than 1. If 2 indices share a number that's greater than 1, that they're both divisible by, then you can actually make a path, right? So for these 2 nodes, they are both divisible by 2, so you can make a path. And so you can actually go through, we're going to go through every prime factor, and we're just going to go down the list, and for every single pair of edges in the list, we're going to make a path. So we're going to make a path here, and we're going to make a path here. And so what would that look like? So if we actually draw a graph, right? So there's a path from 0 to 2, and there's a path from 1 to 2. Well, now that's a fully connected graph, because when we call union find on 0 and 1, that's going to return. If we check if they're connected, that's going to be positive, because let's just say it looks like this, right? Where the parent of all these is this. So if we call union find on 0 and 1, the parent of 1 is going to be 0, the parent of 0 is going to be 0, so that'll be true. And then we're going to call union find on 1 and 2, same thing. Union of 2, or parent of 2 is 0 and parent of 1 is 0, so that's going to be true. And also, what would be the time complexity, right? So for every single prime factor, you can have every single edge, technically, but that'll just be some constant value times the number of edges. So this is actually just going to be like, like some whatever constant value. It shouldn't be too big, because when these numbers grow big, the number of prime factors don't increase that much, right? So prime factors would be like 2, 3, 5, 7, 11, 13, but then afterwards, like there aren't too many numbers that are prime. So this number should be relatively small, even to get to this 10 to the 5th, right? So we can do a little bit more. So we think it's like 19, 23, 29, I think, and so on. And as you can see, as you go up, the distance between all these prime factors is smaller and smaller and smaller, and so, or bigger and bigger and bigger. So there's not going to be that many prime factors. So the complexity of this kind of solution would be actually there's a better way to do it, by the way. So the number of prime factors a number can have is actually square root of n, I believe. Because I'll show you why that is when we actually look at the prime factor method. But to do the prime factor, it's going to be square root of n time. And so now our solution, instead of being n squared, is going to be n square root of n time. And union find is just constant time. So all these union find connect and whatever, and we're traversing through the graph as constant time. So now we kind of know the plan. First, we're going to do the prime factorization of every single number, and then we're going to go through this dictionary of prime factors, and we're just going to connect everything in there. And then all we're going to do is we're going to just connect. We're just going to check every pair of edges. So we don't have to check every. So remember when we have some edges like this, right? 0, 1, 2. Let's say these are the indices, by the way. So we don't have to check all of them. All we have to do is just check edges that are next to each other. So we check this, we check this, we check this, which would be constant time. And if there's ever any gap, that means we can't get from one edge to the other, because if there is a gap, that means that everything connected to this edge and everything connected to this edge don't meet. So you can't ever get from every single node to every single other node. Okay, so hopefully that makes sense, and let's take a look at the code, and I'll try to explain the complexity from there. And then I will also provide a link to the union find. So Typically, I think I actually wrote the union find in some other problems I made, but for this problem, this is basically a copy paste of the standard union find on LeetCode, and I'll just explain it really quickly. So every single node, there's an array, and every single node starts out with being its own parent, and there's also a ranks. And the reason that the ranks are used is because for union find, we have to actually see, like I said before, right? We have to actually see, like, let's say we try to connect this node to this node, maybe. We have to see, okay, well, which tree is longer, and then we're going to connect the shorter tree to the longer tree, because that would minimize lookups. So if we're trying to find a parent of something, like if we do it the other way, if we connect this tree to this tree, let's say, right? So if you look, this longest path is 5 nodes, and this longest path is still 4 nodes. So that's why you have these ranks. It minimizes search times. And then find, like I said, simply finds the parent of the node that we're at. And then what union does is if it checks the parent of both nodes, and if they're not equal, then it combines them together. So it simply makes the parent of the shorter path the longer path. And then we have this connected that's pretty straightforward. It just checks if 2 nodes are connected. So it gets the parent of 2 nodes, and if they're not the same, then it returns false. Okay, so now let's take a look at our solution. It's actually not too tough to code, I would say. The only problem is, I would say, for this LeetCode, the way they made the time complexity, it's really tight to get it to pass. Like if you do anything a little bit off, like I actually had this prime factorization method that I'll talk about to get the prime factors a little bit different, and it wasn't passing because it was a little bit off, which is probably kind of silly. Like the time complexity is still going to be the same, but for some reason, they wanted to make it like this where it barely passes. So if you get something where it's failing, I think mine was failing the last test case. That means you're probably just going to want to make a few little optimizations in your methods, or you can just say, well, that's good enough. Like I'm probably using the right kind of stuff. And in a real interview, it's not going to matter. Like the time and space complexity will be the same. Okay, so let's look at this. So we have this visited, and this visited is the prime factors. So it's going to be a default dict of lists, and this is going to be the prime factors. So let's actually take a look at this prime factorization method, and maybe let's look at it for a few numbers. So let's say we have a number like, what's a good number? Like maybe 72 or something. So let's take a look at how we get the prime factors of 72. So we have 72, right? Okay, and so we create a set that's going to be our output. And we don't need to go past the square root of the number, because the biggest number that we're going to have to check is the square root. So let's say we have a number like 25. The biggest number we're going to have to check is 5, because anything bigger is going to be multiplied by something smaller than the square root, and we're going to handle that down here, where if we have some number that's greater than 1 that we have left over, so we're going to handle it down here. So let's take a look how this works. So we have 72. So we say 4, and then the square root of 72 is like, what, like 8 and something. So and then we just round up. So we're just doing to 9, or actually we're doing to 8. The square root of, so we're doing to 9. Okay. Anyway, so what we need to do is we need to say, while the number is not 0, or sorry, while we can divide it by this number. So let's say we start dividing by 2, right? And we say, okay, is the mod 0? Yes. So then we're going to add that number, and that's right? So we're going to add 2 here. And okay, so we divide it by 2. So now what do we have? So we're at 36, and we keep dividing until we can't anymore, right? So we keep dividing and we keep dividing, and we can add it to the set, and that's why we're using a set, because we're going to keep adding 2 and we don't want duplicates. So it'll divide 18, divide 9. Okay, so now we have 9. Now we increase this I, right? So this I will be 3. Then we divide, and we get 3, and then we put in a 3 here. And then we divide by 3, so it'll be 3. Then we divide by 3, and it'll be 1. And now what we do in the end is, if we do have some remainder, we add the number, because let's say we have some number like 17, right? We can't divide it by anything, so we have some kind of remainder on here. And so 17 would be the square root, right? It would be like 4. It would check 1 through 4, and then it would have a remainder, so it would add the number. So you could look this up. There's a bunch of YouTube videos for prime factorization, but that's the basic, straightforward ways. You start at a small number, you keep dividing until you can't, then you increase and increase and increase and so on. So now that we get this prime factorization, it's pretty straightforward from here. So all we're doing is we are iterating through every single one of these numbers, right? So 2, 3, 6. So let's just show you this. So 2, 3, 6. We're iterating through every single one of them, right? So we're here. And then we get, and then remember, our prime factorization is going to return a set of the numbers that it is a prime or that are the prime factors. So for every single index, we iterate through the set of outputs, and then we simply go to that index. So like, let's say our set of outputs is 2, 3, 5. Then remember we have this visited dictionary, so let's just say v, and then all we do is we iterate through all these prime factorizations, or prime factors, and then we add the index of that number to those, right? So 2, whatever list that has, we'll add I. 3, whatever list that has, we'll add I, and so on. And so that's pretty straightforward. And then from here, now we have our visited set, so now we make this union find data structure. And all we do is for key and visited, and remember key is every prime factor. So in this case, the prime factors would be 2 and 3. All we do is we just loop through the list of items. So let's take a look what that would look like for this case. So remember for 2, 3, 6, our prime factors are going to be 2 and 3, and the indices for those are going to be, so for 2 it's going to be 0 and 2, and here it's going to be 1 and 2, right? And so we're saying for every single key, so we're at key 2, take the two indices right next to each other and connect them. So we're going to connect this, then we're going to connect this, right? And then that's what's that going to look like once again? So 0, 1, 2. So there's a 0, 2. There's a 1, 2. Now, once we connected them over here, now we just loop through all of the indices, and we check the indices that are right next to each other, and we say if they are connected, or if they're not connected, return false. Because like I said, all we have to do at the end is we just do a linear search through all the indices when we compare the neighbors, and if they aren't connected, we return false, and at the end we return true. So let's look at this example actually for how this would run through this last example 3, and then we'll be done. And we'll look at the space and time complexity as well. So 4, 3, 12, 18, or 8. Okay, so let's just look at this. So for 4, the prime factors is only 2, so we're going to do this. It's going to add index 0. For 3, the prime factors is only 3, so 3 is going to add index 1. For 12, the prime factors are 2 and 3, so that's going to add index 2. And for 8, the prime factors are 2, just 2, right? So that would be 3. Okay, so this is what our visited is going to look like. Now remember, we're going to go through every key. We're going to make a path between close edges. So we're going to make a path here, make a path here, make a path here. Show what that looks like. So 0, 1, 2, 3, let's call it. So there's a path 0, 2. There's a path 0, 3. And there's a path 1, 2. And so you can see that when we check 0 and 1, they are going to be connected by doing union find. 0 and 2, or sorry, 0 and 1, 1 and 2, they are going to be connected, and 2 and 3 are also connected because there is a path connecting all of the nodes on the graph. And for something like 3 and 5, there would just be no path. So let's think of the time and space complexity here. Okay. So for union find, by the way, I believe the find and the union and all these things are big O of 1, or I think they're pretty close to big O of 1 time because they are trying to make it with this rank, they are trying to make it pretty optimal. So I think that's around big O of 1 time. It's not exactly, but it's around there. Okay, so what are we doing? So we're doing this prime factorization for every single node. And so remember, prime factorization, the complexity is going to be square root of the number, right? Because we're doing 2 to square root. And then we're doing that n times. So it's going to be square root of n times to get all these prime factorizations. And then from there, we're just simply doing a linear search. Or there's going to be maximum n square root of n things that we have to connect as well. And then for this part, when we're going through the nodes and we're just checking if they're connected, that's a linear search. So that's big O of n. And so this is going to be the main thing, getting these prime factorizations and making sure that they are connecting them all. That's going to be n square root of n. Okay, and for space, so we do have this prime factorization thing, right? And there can be square root of n prime factors, and there can be n in each one, so that'll be the same thing. So n square root of n, right? And there can be a square root of n prime factors, and then in each prime factor, the worst case scenario is it has every single node. And as far as union find, that's just big O of n because we have a root array that's equal to big O of n. We have a rank array that's equal to big O of n, and that's all we're using. Okay, so yeah, and like I said, we can try to submit this, but you can, so I'll actually show you this as well. So this problem for me barely passes. If I change a little bit here, it'll be too slow. And you could see that it's beating 50% and 80%. So they make it really close to passing, which is kind of annoying. It's not the best interview type thing because you can have a solution with the same complexity as mine, but you just have a little bit of stuff off. And so yeah. Okay, so that's it for this problem. And if you liked it, please like and subscribe to the video, and I'll see you in the next one.